If the characteristic equation of a real matrix A has some complex roots, then these roots provide critical information about the matrix A. The key is to let A act on the space Cn of n tuples of complex numbers. The matrix eigenvalue eigenvector theory already developed for Rn applies equally as well for Cn, such that a complex scalar lambda satisfies the determinant of A minus lambda times the identity matrix equal to 0 if and only if there is a non-zero vector x in Cn, which is complex, where Ax is equal to lambda x. We call lambda a complex eigenvalue and x a complex eigenvector corresponding to lambda. Example, let's let A be this 2 by 2 matrix, then the linear transformation from x to A times x on R2 rotates the plane counterclockwise through a quarter turn. The action of A is periodic, since after 4 quarter turns, a vector is back to where it started. No non-zero vector is mapped into a multiple of itself, so A has no eigenvectors in R2, meaning no real eigenvalues. The characteristic equation of A is lambda squared plus 1 equals 0. The only roots are I and negative I. Remember, I squared is equal to negative 1 when you're working with complex numbers. So negative 1 plus 1 is 0. Negative I times itself would be positive I squared, which is negative 1 plus 1 is 0. But if we allow matrix A on the complex number C2, well, it's not a complex number, but anyway, it's the C2, then if we take matrix A times 1 negative I, that's going to equal I1. 0 times 1 plus negative 1 times negative I, that's I. 1 times 1 plus 0 times negative I, that's 1. Now, like similar to what we did in previous sections, if you take an I out, which is one of our eigenvalues, I times 1 is I times negative I is negative I squared, which is negative negative 1, making it positive. So this is an eigenvector corresponding to this eigenvalue. Now, since we have two eigenvalues, if you repeat and you do A times 1I, this time it's positive, then you're going to get negative I and 1. Pulling out a negative I gives you that vector back, so eigenvalue of negative I has a corresponding eigenvector of 1I. Let's look at another example. We're going to let matrix A be this 2 by 2 matrix, and we're going to find the eigenvalues of A and a basis for each eigenspace. Okay, our characteristic equation is going to be 0 equals the determinant of matrix A minus lambda times the identity. So if we take matrix A and we subtract a 2 by 2 matrix where the main diagonal is lambda, the other diagonal is 0, then we're going to get 0.5 minus lambda. These two entries are going to remain the same because all you're going to do is subtract 0. It doesn't change them. 1.1 minus lambda. Now, remember, determinant, if you don't write DET, you use vertical bars. Okay, so this diagonal multiplied together minus this diagonal multiplied together. If you carefully FOIL and combine like terms, you will get 0.55 minus 1.6 lambda plus lambda squared. This part back here, when you subtract this negative product, it will make a positive 0.45. And you can check out with your calculator. Combining 0.55 and 0.45, you get a 1. So this step, all I did was write all the terms in descending order and combined these two constants. Now, because this equation you can't solve by factoring with whole numbers, we're going to use the quadratic formula. Remember, a is the coefficient of your squared term, b is the coefficient of the linear term, and c is the constant. So we have a is 1, b is negative 1.6, and c is 1. So when you put this through the quadratic formula and simplify, you will find that one of your eigenvalues is 0.8 plus 0.6i, and the other eigenvalue is 0.8 minus 0.6i. If you take the eigenvalue with the minus sign, a minus lambda I, matrix A minus lambda times the identity, subtracting the same positions, 0.5 minus 0.8 is negative 0.3 minus negative 0.6i. That maybe should be a positive. I'll check here in a minute. I think it is. And then 1.1 minus 0.8 is 0.3 minus a negative 0.6i is positive. So this is the 2 by 2 matrix you get after a minus lambda I. Now we're going to solve a minus lambda I times vector x equals 0. And since we're working in a two-dimensional space, x will be x1 and x2. So I'm going to take that difference, matrix A minus lambda I times x equals 0. Now, with complex numbers, I don't know how well a calculator will row reduce echelon form this to give you a clean x1 or x2, but just translating it out, negative 0.3 minus 0.6i times x1 minus 0.6 times x2, 0.75 times x1, 0.3 plus 0.6i times x2. Okay, I'm going to solve for x1 in the second equation. You can pick either equation and either x1 or x2. So you don't have to do it this way, but you do need to commit to one equation and one unknown. I just happen to pick 0.75 x1 as my target. So I'm going to solve for x1 in the second equation and let x2 be a free variable. Alright, so I'm going to take this equation and solve it for x1. 0.75 x1 plus 0.3 plus 0.6i times x2. If we carry these terms over, they're all positive right now. If you move them across the equals, they're going to go negative. Dividing each term by 0.75, negative 0.3 divided by 0.75 is negative 0.4. Negative 0.6i divided by 0.75 is negative 0.8i. And this is still times x2. Now, because x2 is a free variable, you can randomly pick a number for your x2 value. The reason I'm going to pick 5 is I know if I multiply both of these terms by 5, 0.4 times 5, if it's negative 0.4 times 5, you get a negative 2. Negative 0.8i times 5 is a negative 4. Basically, I just wanted to pick a number so that I didn't have to deal with decimals anymore. V1 is the eigenvector, or a basis for an eigenspace, for lambda 1, and I chose that as lambda 1. So x1 is negative 2 minus 4i. x2 was free, but we let it be 5 to help eliminate the decimals. If you repeat with similar steps for the other eigenvalue, the 0.8 plus 0.6i, and you repeat all those steps from the first slide, you'll get the second eigenvector, which is a basis for the eigenspace, as negative 2 plus 4i and 5. I also let x2 be 5 for this one, because 5 times both of these numbers will become a whole number or an integer instead of a decimal. Okay, so let's note that our eigenvalues, the first one we used was 0.8 minus 0.6i. The second one is 0.8 plus 0.6i. Those had corresponding eigenvectors of these two and their conjugates. Notice that these two eigenvalues, one has a minus, one has a plus, those are conjugates of one another. You switch the sign in the middle. That also shows us these two vectors are conjugates in the top position. Definition: the complex conjugate of a complex vector x in Cn is the vector x bar. This is the notation for a conjugate, whose entries are the complex conjugates of the entries in x. The real and imaginary parts of a complex vector x are the vectors, and we're going to call the notation as rex, so the real part of vector x, and the imaginary part of vector x, and Rn formed from the real and imaginary parts of the entries of vector x. So your vector x will have a real part and an imaginary part. The imaginary part will have an I stuck to it. Example: suppose your vector x is 3 minus I, and 2 plus 5i. If you strip off the real parts, you have 3, 0, and 2. The real part of vector x is 3, 0, 2. The coefficients for I are negative 1, 1, and 5. So that imaginary part will have coefficients negative 1, 1, and 5. The conjugate of x is to switch the sign in the middle. So you still have the same real part, 3, 0, 2, and the same imaginary coefficients, negative 1, 1, and 5. But you have a minus sign instead of a plus sign to be a conjugate. Putting those together, 3 plus I, 0 minus I, 2 minus 5i. The next example provides the basic building block for all real 2x2 matrices with complex eigenvalues. If matrix C has this form, main diagonal A's, the other diagonals B, top one being negative, where A and B are real and both are not 0, then the eigenvalues of C are lambda equals A plus or minus BI. A, you take these values, put here. B, you would take the lower left. Also, let R be the absolute value of your eigenvalue. And if you remember from trig, that's going to be A squared plus B squared. Matrix C can be written as R times A over R, which is just A, R times B over R, which is just B, and so forth. So basically, that will translate to a main diagonal of R, which is the hypotenuse. I have a geometric shape down here I hand sketched. Cosines on the main diagonal, sine on the other diagonal. Phi, or phi, however you want to pronounce it, it's the angle between the positive x-axis and the ray from the origin to the point AB. The angle, excuse me, y'all, the angle is called the argument of the eigenvalue. The transformation from vector x to c times x may be viewed as the composition of a rotation through the angle phi and a scaling by absolute value of lambda. So maybe you have a vector x, the amount it's rotated is the phi or the phi, however you want to pronounce it. If there is any shrink or expansion, then that's called the scaling. Now let's uncover the rotation that is hidden within a real matrix having a complex eigenvalue. So let's take matrix A. It's a 2 by 2. We're going to pick one eigenvalue, 0.8 minus 0.6i, and the corresponding eigenvector is -2 minus 4i and 5. This looks very familiar. It was the second example we did. Before we get started too far, let's look at a theorem. Let matrix A be a real 2 by 2 matrix with a complex eigenvalue of A minus BI, where B is not 0, and an associated eigenvector V that's in the complex 2, C2. Then matrix A can be written as P times C times P inverse, where P is a 2 by 2 matrix, in this case, of the real part of your eigenvector and the imaginary part of your eigenvector. So you're going to have reals and imaginary parts. And matrix C has this form: A on the main diagonal, A is the real part of your eigenvalue, and then B on the other diagonal, and that's the coefficient of I from the imaginary part. All right, so back to our example. Go to eigenvector 1. The real parts are -2 and 5. That's our first column of P. The imaginary parts from the eigenvector are -4 and 0. There's no I term down here. -4 and 0. So C, let's be very careful here. If I want to isolate C, I have to multiply from the left by P inverse. P inverse times P will cancel. P inverse times A is that part. To strip away P inverse, I'm going to right multiply both sides by P. P inverse times P will be canceling. A right multiplied by P, so that tells us if we solve for C that we left multiply by P inverse, then we right multiply by positive P, or just simply matrix P. Carefully write in, use your calculator, P inverse, so you're going to type this in as one of your matrices. C is what we're after. So if you invert this one, you get 1/20 times this 2 by 2, and that's from switching and reversing signs. Matrix A was given, and then P left alone goes here. P inverse times A times P. Using a calculator, that gives us matrix C, which is 0.8 on the main diagonal, 0.6 and -0.6 on the other diagonal. Fits that description perfectly. Also, A, the real part of the eigenvalue, and then B, that's the coefficient of the imaginary part. And an additional example, show that if A and B are real, then the eigenvalues of matrix A, which we just looked at a diagonal case of that, where real part, imaginary part, that's A plus or minus BI, with corresponding eigenvectors, one negative I and one positive I. Okay, so from previous sections, we looked at, if you just wanted to verify, you multiply them. So we're going to take A times V1, matrix A times eigenvector 1, carry out the multiplication, A times 1, negative B times negative I, that's A plus BI, B times 1, A times negative I, that's B minus AI. If you were to pull out A plus BI, because that's one of your eigenvalues, that will leave you with 1 minus I. That's exactly what eigenvector 1 is. So that tells us that A plus BI is an eigenvalue, and this is its corresponding eigenvector. Do the same thing with matrix A and V2, eigenvector 2. If you multiply the same way, A times 1, B times negative I, B times 1, A times I, and you pull out A minus BI, that leaves a 1 and an I. Be very careful here. A times I, negative BI times I is negative B I squared. I squared is negative 1, so negative B times negative 1 is positive B. Just be careful you convince yourself. This is the eigenvalue pertaining to this eigenvector. So your eigenvalues are A plus BI, A minus BI. Those are conjugates. And then these two are the corresponding eigenvectors. And so we've just shown that V1 is an eigenvector of this eigenvalue, and V2 is an eigenvector corresponding to the conjugate of lambda. I do want to mention that this section also, in your Google Drive folder, I did put both this lecture set of notes that I voiced over and examples of how to do the homework in there. You will see those as, let me pull it up real quick. In your Google Drive folder for Unit 4, this is the last section of Unit 4. This one is called Complex Eigenvalues. So you'll see it in Google Drive as labeled with a number 5, Complex Eigenvalues. The homework examples I put as 5A, Complex Values Homework. And hopefully between some of this explanation and being able to look at the homework, you'll be able to get enough examples to show you how to finish your homework. And then since this is the end, you'll have a Unit 4 test on my math lab. What's coming up after this is we're going to do a Unit 5, and it will have 3 sections, and then that's going to be it for the course. So let me know if you have any issues come up, and just keep hanging in there. You guys are doing fine, and I appreciate your hard work.